Okay, so good morning again. So we will again start with where we left. We were working on constitutive equations for a rod. Constitutive equations. And the idea was we wanted to relate the forces and moments with the kinematic variables, isn't it? Because the equations that we had derived, n prime plus n hat equals 0 and m prime plus r prime cross n plus m hat equal to 0. So these equations have n and m, and we don't know how they are related to small r and capital R, the kinematic variables. So that's why we are talking about constitutive equations. And then we use frame indifference and finally came to this form of constitutive equation, psi of r transpose small r prime comma big R transpose big R prime. So that's the strain energy or stored energy per unit undeformed length, right? And then we also said what's the physical meaning of this. So if we say this is V, then these were actually the components of little r prime, which is the center line tangent, in the frame of directors. And we also found that this, if we write it as V1, V2, V3, then the first two components are the shears and the last is axial stretch. Okay? And then we wanted to understand the meaning of the other argument over here. So that's the first argument. Now we want to understand the meaning of the second argument. Now as rotation, if this is a rotation matrix, this quantity is going to be a skew symmetric matrix, isn't it? Something that we had worked out last time. I can also show you very quickly. So R transpose R is equal to identity. So then you take the derivative on both the sides and you get R transpose prime times R plus R transpose R prime equal to 0, which means R transpose R prime is equal to negative of R transpose R prime transpose. So here I got a matrix which is negative of its transpose, so it's a skew symmetric matrix, right? So that means it's a skew symmetric. So let's define it as big K, which is R transpose R prime. And we write it as 0, 0, 0 minus K3, K3, K2 minus K2 minus K1 and K1. Okay? And the reason I define it like this is because its axial vector. So the axial vector of k, which we denote as little k, will then come out to be simply k1, k2, k3. Okay? So that's my axial vector. So that's the reason why I define my big K like this. And what's the relation between this big K and its axial vector little k is that if you say big K times any vector A, then it is simply its axial vector k cross A. Okay? All right. So now we want to understand the meaning of these three quantities here. What is K1, what is K2, what is K3? And we will see that they in fact are bending curvatures and twist. K3 for example is twist, and K1, K2 are bending curvatures. Let me give you the example of twisting. So if I say twisting of a rod, so if we have a circular rod for example, so that's a circular rod, and if you twist it, then the axial lines become helical, isn't it? So it's going to become something like this. And what will be the rotation of any cross section? If I think of a cross section over here, it's simply going to rotate about this axis, which is E3. And if I say theta is that rotation, then that is simply going to be some number. Let's call that let me call it K3 only. Okay, let me call it K3. So it will be some number K3 times S, the arc length, right? Big S. And then we know that this K3 is nothing but the twist, right, from our strength of materials course. So K3 is actually the twist. So what will be my rotation matrix big R? What is that going to be for this particular case? So since the cross sections are all rotating about E3 axis, the rotation matrix simply becomes 0, 0, 1, 0, 0, cosine of K3 times S minus sine of K3 times S, then sine of K3 times S, and cosine of K3 times S, right? Isn't that the rotation matrix? And then if you talk about your little r, what's your little r? If there is no stretching, if you are just twisting, then little r is simply S times E3, isn't it? It's simply S times whatever it was earlier, because I'm not stretching it. Okay, maybe I should write capital S here. Okay, then what is then little r prime? It is simply E3. And what's big R prime? So when you do big R prime, these ones all become 0, right? Cosine of K3S, that becomes sine of K3S times K3, right, minus K3, yes. So this becomes minus with a minus sign, okay, minus sine of K3s, and you get a K3 in the front because each of them is going to cough out K3. So, K3 comes out, and minus sine of K3s becomes simply minus cosine of K3s. Then sine of K3s becomes cosine of K3s, and cosine of K3s becomes minus sine of K3s. Okay. All right. So, these are my derivatives of the kinematic variables. Let us then look at what is my V. So, V is simply big R transpose little r prime. Now, big R is a rotation about E3 axis, and little r prime in this case is itself an E3. So, little r prime is pointing along the axis of big R. So, what will you get once you work out big R transpose little r prime? You get back little r prime. It won't do anything to little r prime because it is pointing along the axis of big R, isn't it? So, you will simply get 0, 0, 1 because this is E3, it is 0, 0, 1, right? And then you can extract V1 equal to 0, V2 equals 0, V3 equals 1. So, no shear, no axial strain as we thought earlier, because we did not impose any shear or axial strain. Let us then talk about your big K. What is big K going to be? That is simply big R transpose big R prime. Then you just have to take its transpose and multiply with big R prime. Okay? And you work out the multiplication, and you will simply get K3 times 0, 0, 0, minus 1, 1, 0, 0, 0, 0. Okay? And you see, if you compare this with that K over here, you have that same K3, right. So, from here when you extract your little k axial vector, it becomes 0, 0, K3. So, what this tells you is that the third component is actually denoting twist, right. Similarly, you can also work out the case of bending. When you work out bending, it is going to bend about, let us say, E1 axis. Okay. So, think of, so this was all for twisting, and when you work out bending, so let us say that is your E3 axis, and that is your E1 axis, and what comes out is E2 axis. And if I bend it, let us say, let us suppose I bend my beam about E2 axis. Okay, I am bending about E2 axis. So, it is going to become like this. Bending into a circle if it is a pure bending case. So, the rotations are happening about E2 axis now. Okay. So, if you write down the rotation matrix, your big R, this will then be, since it is a rotation about E2 axis, you have 0, 1, 0, 0, 0, and then you will have cosine over here, and since it is about E2, maybe we call it K2 times S. Okay, so suppose that the rate of change of angle is K2. So the rotation of a cross section at a distance S will be K2 times S. Okay, so that's cosine of K2 times S. Then this becomes minus sine of K2 times S. This becomes sine of K2 times S, and this becomes cosine of K2 times S. And then when you work out your big R transpose big R prime, so you can work out as we did last time and then multiply the matrices. You will simply get 0, 0, 0, 0, 0, and you get a K2 here, minus K2 over here, then 0 here and 0 over here. You can work out and see that's what you will get. And then if you get your axial vector, little k, it comes out to be 0, K2, 0. So which means that the middle component is actually the bending curvature, right? It's the bending curvature about E2 axis. Similarly, you could have bent your beam about E1 axis, and you would have gotten a K1 over here as a first component. And then you can do any general rotation where you have both bending and twisting involved, and you would have gotten everything over here.
Is V in that case?
Yeah, that's very interesting. So if it's a pure bending case, maybe we can work out what's V turning out to be. Can you guess what should be V? If it's pure bending, which means there is no shear and stretch, what should be V? I mean, for any general case, if you have no shear and stretch, what will V turn out to be? So V has got three components, V1, V2, V3. So what will be V? No shear means V1, V2 are 0. And no axial strain means V3 is 1. So are we going to get this when we bend it? So for that you have to first write down the formula for little r, isn't it? So what's the formula for the center line, deformed center line? So as you can see here, I am trying to bend it about E2 axis, so its center is somewhere along E1, right? And let's say the radius is capital R. Okay, and if it's a pure bending case, then if you go S along the center line, so if I go S along the center line, what would be the theta? So if you go S along the center line, so S is your arc length. So that's the arc of the circle, the curved line. So what's theta going to be? r times theta is equal to s, right? So that means that implies theta is equal to 1 over r times s. So this becomes your curvature, right? Because you see the rate of change of angle, that's 1 over r. So that would be your K2 for the case of pure bending. Let's look at what is little r. So what will be little r of s? So we have to get the equation of this circle. So any s is over here. So what's its E1 component, what is its E3 component, and what is its E2 component? E2 is of course 0 because it is bending in E1 E3 plane, and E1 component will be E1 component, you take its cosine, that's over here, and subtract your big R, right? So if I can write it, then E1 component is going to be big R into 1 minus cosine of K2 times S, isn't it? When S is equal to 0, 1 minus 1, 0. So it's at the origin. And little r2 is 0, second component is 0, and the third component you just have to take the sine. So that's sine, of course big R also. So big R times sine of K2 times S. So what's your little r prime? So that's going to be big R coming in the front, and then you take its derivative. So cosine becomes sine minus one more minus, simply becomes sine, and one K2 also comes in the front, K2 and the last one becomes cos of K2. Okay. And then what's your V? So V is now big R transpose little r prime. So let's have my big R over here with a transpose. So it's a rotation about 2 axes. So that's something I have already there, 0, 1, 0, 0, 0, and I need to get the transpose. So the signs are just going to flip. So you get a minus over here and plus sign over here, and cosines remain wherever they are. So that's the R transpose, and you multiply this with little r prime. So you have sine 0 cosine, and of course you get kappa 2 times r in the front, kappa 2 times r, work out the multiplication, 0, right? Again 0, sine square plus cosine square, 1, and big R is 1 by kappa 2, or kappa 2 is 1 over big R. So this also becomes 1. So what you get is 0, 0, 1 as you expected, right? So everything works out very well. Okay, and you can work out even complicated deformations. You will get what's expected. Okay, so we have now understood what's the meaning of the arguments over there, isn't it? So we have introduced two strain measures. So these are strain measures. V equals big R transpose little r prime, and K equals axial vector of big R transpose big R prime. So these are our strain measures, and your strain energy then depends on these strain measures V and K. So that's your objective strain measures, frame indifferent. Okay, still our goal was to relate the forces and moments that we see over there with the kinematic quantities. We still haven't achieved that. We just got some idea about the psi. How should the psi look like? What all should it depend on? So we found out there are 6 quantities, 2 shears, 1 axial stretch, 2 bending curvatures, and 1 twist. Total 6 strain measures. Okay, so the next question would be, can the derivative of the psi with respect to the strain measures be somehow related to forces and moments? Because you see, in 3D elasticity, when you take the derivative of stored energy with respect to deformation gradient, you get the stress, right? First pK. So you take derivative of stored energy with respect to any strain measure, you get the conjugate stress, right? So here also, if I take the derivative of strain energy with respect to these strain measures, I should get some conjugate stress resultants, because these are not the usual 3D strain quantities, right? So these are some resultant strains, so I should get some resultant stress. So your N and M, the forces and moments, are actually your resultant stress. Force is simply integration of stress over the cross section, right? PE3 dA integrate over the cross section, and moment is the first moment of the stress. So it's some resultant of a stress. So we hope that its derivative should give us the forces and moments. So that's the next thing we want to prove. Okay? So that's going to be a little longer exercise, but I think it's a nice thing to work out. So we will use what's called the principle of minimum potential energy to prove that its derivatives do give us the resultant stress. Minimum potential energy. So you all know that if we use the principle of minimum potential energy, so we write down the expression for potential energy of a rod, take its first variation with respect to kinematic quantities, then it's going to give us the Euler-Lagrange equations, right? And that Euler-Lagrange equations should somehow be related to the equations that we got from direct application of Newton's law. So when we compare those two, that's where we will identify that yes, the derivatives of strain energy with respect to the strain measures gives us the forces and moments. So let's work out a simple situation of a cantilever, and you could do it for any other case also. So we have a cantilever and we are applying a load here, let us say P, E1. So, what's the total potential energy of this rod? So, if I denote my potential energy by, let us say, P, can I use P or should I use, sorry?
Why don't you use
Pi? Okay, yes, pi, yes. So, that's going to be equal to the strain energy of the rod, which is simply the integration from 0 to L of psi of V comma k ds, right, because this was strain energy per unit undeformed length. So, you integrate it over the length, you get the total strain energy, and you see your V and k can vary along the length, right, it need not be constant. So, that is just the strain energy, then you subtract the work done by the external load to get your potential energy, right. So, I have to do minus P E1 dot big little r of L. Can I write this? So, that is the work done by the external load. So, what is the work done by this load, for example? That is simply force times the displacement of the point of application of the force. So, it is acting at this tip. So, what is the displacement of the tip? That is simply r of L minus LE3. That is the displacement. So, work done will be force dotted with this displacement. But then we have, so we have an extra constant quantity also, PE1 dot LE3, so that anyway cancels. But you can also always remove a constant quantity, that does not matter, right. So, I hope you understood why is this the work done by the external load. Force times the displacement of the tip, which is RL minus LE3, right? Yes?
The interesting point is minus, no? To understand
Yeah, interesting point is minus. Why it comes with a minus sign?
why we lose potential.
Yeah. Can you say something about that?
Yes.
Yeah, that's always a point of confusion, why it comes with a minus sign.
The potential is the potential to perform work. No? If you think of let's say, put a bucket full of water under the ceiling, then it has a potential to perform work. The potential is, let's say, height times weight. So the force of that bucket points downwards. So if you move the bucket downwards in the direction of its force, it's coming lower, so it loses potential to perform further work. It will hang lower, so it has less potential to perform work because it has lost height. So it has moved in the direction of its force. So it's the same as saying P times R is the work, so to speak, that is performed or that is lost, let's say the potential that is lost among moving the weight in its direction.
Yeah.
So you have less potential, that's why you have minus.
Okay. And another way I could say is, I'm not sure whether that is correct, but I think there is no ambiguity there. Here, this rod is not a closed system, it's not remaining on its own. So, it's interacting with the environment through this load P, isn't it? So, we have to think of a closed system. So, think of this rod and the person who is applying this load, and then you write the energy of that closed system. So, this part is the energy of the rod, and this part is the energy lost by the person, because he did some work on the rod, so he lost some energy. So, his energy reduced, therefore, it comes with a minus sign. So, that is the total energy of the closed system, and that is something we should minimize, right. Okay. All right. So, that is the total potential energy, and what does it depend on? So, it is depending on my kinematic variables, which is little r and your big R. So, you see, it is a functional, its energy is a function of a function. So, it is a functional. So, therefore, we have to take variation, right. So, I think you have done variational calculus. Okay. So, but here it is going to be a bit tricky, because we want to vary these kinematic quantities, which is not so easy. So, little r, how do you perturb your little r? How do you vary the little r? So, little r is a center line. You want to change your little r and see whether the energy has increased or decreased. So, that you could do by saying that little r of epsilon is your little r plus epsilon times some delta r. So, delta r is then the fluctuation in little r. That is also going to be a function of s, by the way, and epsilon denotes the magnitude of fluctuation. So, that is quite okay, but how to vary your big R? So, that is really tricky. So, you see, we want to work out the most general case. So, your rod could have come in the 3D configuration, and then it has some big R, and I want to impose some extra fluctuation in big R on top of whatever is existing. So, can we write it as some big R plus epsilon times some delta big R? Can we do that? So, that is something we cannot do, because I want the fluctuated big R also to be a rotation, right, because it has to be a rotation when you perturb it. But it is not necessary that if you have a rotation matrix and you add anything arbitrary and you still get a rotation matrix. That does not happen. So, this is not correct. So, you can't perturb your rotation in this way. So, that is the most tricky part in this perturbation. Otherwise, everything is as it is in 3D elasticity. So, the way to perturb this is you have to think of imposing extra little rotations on top of this big R. And the way to do that would be simply you write that this is equal to some exponential of epsilon delta theta. I will tell you what does that mean, into your big R. So, this is the fluctuation in big R, which is applied on top of existing rotation, and this delta theta with a 2 tildes below, it is a second order tensor, and it should be skew symmetric. You remember your axis angle representation. So, that is the axis angle representation. So, delta theta, so when you get your little delta theta, the single tilde, this is axial of this skew symmetric delta theta that you have over here. Okay. So, the direction of this little delta theta tells us the axis about which I am applying that extra rotation, and magnitude of delta theta with epsilon tells us the angle by which I am applying that extra rotation. Okay. So, for example, you have this existing big R about some axis, let us say that is your axis A, and then you further apply this extra rotation about a different axis, which is delta theta divided by the magnitude of delta theta. Because I want a unit vector. So, that is the axis about which I am applying that extra rotation, and the magnitude is epsilon times the magnitude of delta theta. So, in this way you can always perturb the rotation accurately, because now you have this as a rotation, because exponential of a skew symmetric matrix always gives me a rotation multiplied with another rotation. So, multiplication of two rotations are always rotations. So, that is the most tricky part here. So, you see what you have to perturb, what is the perturbation quantity, that is your delta theta. As you change delta theta, you change the axis of perturbation. As you change the magnitude of delta theta, you change the angle of perturbation. Okay? All right.
Maybe we could also explain this particularity of large rotations, that they don't commute.
Yeah,
if you
yeah,
have
yeah.
a box,
Of course.
like a rectangular box with three different lengths, and then
Yeah, that's
you
the
reverse the
order
sequence
of,
of rotations.
yes.
You don't get the same.
Don't get the
result.
same thing. Yeah.
Might help.
Yeah.
Do we have this?
That rectangular thing. Yeah, maybe I could use.
Was this strong? Do we have a sponge? Like a sponge?
Oh, sponge. Yeah, that would be a perfect thing. Yeah.
It's just getting a specimen.
Okay. Yeah, Professor Steinman was just telling me that it is good to say that rotations in 3D do not commute, because when you have planar rotation, you rotate by, let us say anything is rotating about the vertical axis, you rotate by theta 1 and then rotate by theta 2. So, total is theta 1 plus theta 2. So, you could reverse the order of rotation. So, you first rotate by theta 2, then by theta 1, it is still theta 1 plus theta 2, right, it is the same rotation. So, rotations about a given axis always commute, but when you do rotations about two different axes, which means you first rotate by, let us say this vertical axis and then rotate by the horizontal axis, it is not the same as first rotating by horizontal axis and then rotating by vertical axis. So, we are getting a specimen which we can demonstrate also that rotations in 3D or about two different axes do not commute. Okay. So, here for example, you can't say that this is same as big R times exponential of epsilon delta theta. You can't say that. Yes.
One question about what is the structure of this theta matrix? Like I've never seen that exponential times like a
Epsilon.
Yeah, like an exponential of a matrix that this gives
rotation.
SO3 or a rotation. Yeah. So why? What kind of structure has
Oh, okay.
This matrix and delta theta?
Okay. See, I think last time we had, of course, derived the expression also for that rotation, but see, this delta theta is skew symmetric.
Yeah.
So this is simply 0, 0, 0 minus delta theta 3, delta theta 3, delta theta 2 minus delta theta 2, then negative delta theta 1 and delta theta 1. So that's your delta theta with double. It's a skew symmetric matrix whose axial is this little delta theta, which is delta theta 1, delta theta 2, delta theta 3. Okay. And how do you get the exponential of a matrix? It's very much like how do you get the exponential of a variable. So you'll have identity. So this becomes identity plus.
Yeah, I'm aware of that. Thank you.
Okay, so maybe I can write for others also if they don't know. Plus epsilon delta theta plus epsilon square delta theta square over 2 factorial plus keep on going. Okay, and it turns out it has an analytical formula. The series can be analytically computed, and we had written that Rodriguez formula, if you remember. Okay, so just to demonstrate to you, so I have this cube here. So let us say I first rotate by, so you can see you have a green thing looking on your side and red on the top. So if I rotate first by vertical axis by 90 degree, then rotate by horizontal axis by 90 degree. Okay, so you see that's what you have. So you have to remember what you saw just now, otherwise I could cheat also. Okay. So this is what you have, and that's what I had started with. Now I am going to first rotate by about the horizontal axis by 90 degree, then by the about the vertical axis. So you see you have, so it's now pointing along your direction. Earlier it was not the case, right? So right now it is pointing that way, but when you do about vertical axis first and then about horizontal axis, so it's pointing upward. So you get something else, right? So that's a very nice demonstration of the fact that rotations do not commute. Finite rotations do not commute. Okay. All right. So once we know how to perturb rotations, then you can just crank your first variation formula, which is of course is not so easy in this case. So, you have pi times r epsilon comma big R epsilon equals 0 to L psi of V epsilon comma K epsilon. See, as you change your kinematic quantities, V and K will also change because they depend on little r and big R. So, it becomes V epsilon K epsilon ds minus P E1 dot little r epsilon of L. All right. Okay. So, and what we want to do is we want to take the first variation, which should be same as doing d pi over d epsilon at epsilon equal to 0. You know, this epsilon thing is really nice. It converts your variation into simple differentiation. And simple differentiation is something that we all know how to work out. Anyways, so this is the first variation, d pi over d epsilon at epsilon equal to 0. So, when we look at it here, this is 0 to L. Now, we have to use chain rule. So, this becomes del psi over del V at these arguments dotted with your dV epsilon over d epsilon at epsilon equal to 0. Right, simple chain rule, plus del psi over del k dotted with dk epsilon over d epsilon at epsilon equal to 0. ds minus P E1, see, it is a constant. So, it does not get any epsilon here because it is a constant. Whatever the load that you are applying, that you are not changing while perturbing. So, it remains P E1 dotted with d r epsilon over d epsilon at epsilon equal to 0. Okay. So, what we need to get here is this dV epsilon by d epsilon and dk epsilon by d epsilon. So, they are really tricky. So, let me work out this V epsilon. So, what is V epsilon? Very simple, big R epsilon transpose little r epsilon prime, isn't it? V was r transpose r prime, so epsilon will be the epsilon of them, which is, now what is big R epsilon? You have to see on the top, that is your big R epsilon. So, I want to get its transpose, so it becomes R transpose into exponential of epsilon delta theta transpose, right, into a small r prime plus epsilon delta r prime, isn't it? So, that is your V epsilon, and now I want to do dV epsilon by d epsilon. So, what is dV epsilon over d epsilon at epsilon equal to 0? So, So here we got, you see, epsilon is here present, it's present over here also. So you have to use what's called product rule. So you get big R transpose d over d epsilon of exponential of epsilon delta theta transpose, and then you evaluate it at epsilon equal to 0 multiplied by this thing at epsilon equal to 0, because you want to evaluate everything at epsilon equal to 0. So this simply becomes little r prime. Put your epsilon equal to 0, this goes away, plus the other one. So that's going to be simply big R transpose into this thing at epsilon equal to 0, which is identity. Exponential of 0 is identity, like e to the power 0 is 1. So exponential of a 0 matrix is identity. So you get an identity here multiplied with d by d epsilon of this thing, which is simply delta r prime. So what is this then? So this again we have to find out. So we have to have, maybe we can work out over here. So let's work out d by d epsilon of exponential of epsilon delta theta. So you can now do your Taylor's expansion. So we want it at epsilon equal to 0. So this is simply d by d epsilon of identity plus epsilon delta theta plus epsilon square delta theta square over 2 factorial plus blah blah blah, and then you get it at epsilon equal to 0. So what do you think? What are you going to get? This is simply delta theta, right? Because you also have to evaluate at epsilon equal to 0, so higher order terms all vanish. All right, so that tells us what is dV by d epsilon. So dV epsilon over d epsilon at epsilon equal to 0, that's simply R transpose of delta theta into R prime plus delta R prime, right? Oh yes, right. Which is negative, so it becomes negative, because delta theta is skew symmetric. So transpose of delta theta is negative of delta theta. Okay, so that's something we already got. Then we have to get dk epsilon by d epsilon. That's again tricky. Dk epsilon by d epsilon at epsilon equal to 0. So maybe we first work out. So we want to get this. So for that, we will first work out d by d epsilon of big R epsilon transpose big R epsilon prime, because once we get this, I'll just take the axial vector to get that, right? Okay, now doing that again is not so easy. So this is same as d by d epsilon of big R times exponential, sorry, big R transpose times exponential of epsilon delta theta transpose into big R epsilon prime. So that's exponential of epsilon delta theta prime. So into big R plus exponential of epsilon delta theta times big R prime. So of course these comes together, so I could use this curly braces, and here it becomes the big bracket okay. So I just wrote down this R epsilon transpose over here and R epsilon prime over here. All right, then we have to do d by d epsilon. So we are going to use product rule. So first work out this one, then that one. And remember, we have to evaluate at epsilon equal to 0. So that makes our life easy. So this becomes big R transpose, and this is something we already worked out, which is so it comes with a minus sign of delta theta, right? We worked it out. Yeah, over here into this thing at epsilon equal to 0. So what is this going to become at epsilon equal to 0? Any idea what's that going to become? I plus epsilon. So of course this becomes, that becomes 0, right? Yes, this becomes 0, yes, because it's not so easy to see this, but is it easy?
At epsilon equals 0, the exponent is 1.
Oh, and then take the
And
prime. Yes, right, yeah. So we can always reverse it, the order of differentiation. So here is one, you take differentiation with arc length and then d by d epsilon. So you can switch the order also. Anyway, so that becomes 0.
And simply because we put epsilon equals 0.
Yes. Yeah, the question is, can we put it first and then take d by d epsilon? We can't do that, right? So for that we have to say that epsilon and the prime can be interchanged because they are independent. So we interchange and then do first d by d epsilon.
This is the next step. We have applied the d over the epsilon to the first term.
Yes.
And then everything in the bracket we simply.
Oh, yes, yes, yes. So the other one we don't have to differentiate with epsilon. That's right. So we just put epsilon equal to 0 over there. So that's easy, yes. Okay, yeah. Yes. Because so here you see, I first differentiate this quantity with epsilon, and the other one we just put epsilon equal to 0. But when you put epsilon equal to 0, this is identity, take the prime, 0. Okay, so this is not there, and this is simply big R prime. Okay, so thank you. So that's big R prime. Then we work out the second one. So This one we evaluate at epsilon equal to 0. This is simply big R transpose, and then the thing inside the bracket, we have to take its differentiation. So d by d epsilon of this thing, what's that going to become? Anyway, so that's keep that over here. So we'll get something times big R plus d by d epsilon of this thing which we have already worked out, that's delta theta times big R prime. Right, so we have to evaluate this. So maybe we can work out so to do that you have to Taylor expand and then do d by d epsilon. Can you guess what are you going to get? So just do Taylor expansion, take the derivative with respect to prime and apply d by d epsilon. Okay, so we want to get that. That's really hard. D by d epsilon of exponential of epsilon delta theta. Wow. And then you evaluate at epsilon equal to 0. So that's what we have over there. So we do d by d epsilon. Let's do the Taylor expansion. I plus epsilon delta theta plus epsilon square over 2 delta theta square, and we have to take its prime and then evaluate at epsilon equal to 0. So when you take the prime, this becomes d by d epsilon. Identity goes away and this becomes epsilon delta theta prime plus epsilon square by 2 into 2 times, sorry, not 2 times, delta theta prime plus delta theta prime into delta theta plus those things, and then at epsilon equal to 0, right? And then you can see what you are going to get. D by d epsilon equal to 0. What do you get? Delta theta prime. Okay, the result was very simple, but it was not so easy to visualize. So you can write it over here. Okay, and then you see that this first term actually cancels with the last term. isn't it? The first term cancels with the last term. See, we started with such a simple looking thing, and it has so much of things inside. Okay, so that tells me that d by d epsilon of r epsilon transpose r epsilon prime at epsilon equal to 0 is equal to r transpose delta theta prime into big R. But we wanted to get dk epsilon over d epsilon at epsilon equal to 0, which is d over d epsilon of this, of the axial of that thing, of axial of r epsilon transpose r epsilon prime at epsilon equal to 0, which is same as axial of d by d epsilon of r epsilon transpose r epsilon prime at epsilon equal to 0. But the thing inside the bracket, we already got it. So the same as axial of r transpose delta theta prime into r. And what's this equal to? You see, this is also skew symmetric. Delta theta was skew symmetric, therefore its prime will also be skew symmetric. And when you work this out, that's also skew symmetric. You take the transpose, you'll get negative of it. And what's the axial of this? That's simply r transpose delta theta prime, single one. And how do you get that? You can, maybe I can show you. So we have r transpose delta theta prime into r. So if I multiply this with a vector v, or let's say a vector a, then this is equal to r transpose delta theta prime into r a, and then this delta theta prime, because this is skew symmetric, it is same as r transpose of delta theta prime cross r a. Because skew symmetric times a vector is same as axial of this cross product that vector. And then you have this r transpose, you have to put this inside. You can distribute it, it's a proper rotation, you can just distribute. If it were improper, you have to apply a minus sign. So this becomes then r transpose delta theta prime cross a. Okay, so you have something times a is equal to this thing cross a. So that's the axial vector which you have over here. Okay. Prakar, please don't erase everything. So we need, we of course need, so I think we need this certainly. Okay, so I'm just going to write here. Can you erase this part? Yeah. Starting from here. Yes. See, our final motivation is just to show that the derivatives give us forces and moments, and we have to work out so much. But this is also useful at many other places. For example, when you work out the finite element simulation or finite element solution of this elastic rod, you have to get the weak form, take the variation of the weak form. When you take the variation, you will have to take the variation of rotation, you have to take variation of the curvature. So you have to understand these things. Okay, so here's the result. So dk epsilon over d epsilon at epsilon equal to 0 is simply r transpose delta theta prime. All right, so now we can plug in these values in here, isn't it? Can you erase the bottom thing? I guess this is remaining. Okay, so this is then equal to 0 to L del psi over del V dotted with this thing over there, which is R transpose minus of delta theta little r prime plus delta r prime plus del psi over del k dot r transpose delta theta prime. So this whole thing is over here minus PE1 dot d by d epsilon of this thing is simply delta r at L. All right, so then we can see you have this R transpose, you can bring it on the other side and it becomes big R, right? So this is big R del psi over del V dot this thing within the bracket. So we have one delta little r prime and this thing which is minus of delta theta cross small r prime, which is same as small r prime cross delta theta. Right? Plus, again this r goes on the other side and this becomes plus r times del psi over del k dot delta theta prime. So we are almost there. And of course, then you have this minus PE1 dot delta R L. Okay, then what's the next step to be done? So, if you want to get the Euler-Lagrange equations, your delta R and delta theta are arbitrary perturbations. So, what you want to do? You want to have something dotted with delta R plus something dotted with delta theta. And here you have delta R prime. So, you want to transfer this prime on the other quantity, right? So, we could write it as 0 to L R times del psi over del V dot delta R whole prime minus big R del psi over del V prime dot delta R. Okay, so this is coming from the first term over here. Then we look for the delta theta ones, plus 0 to L. Here also we got a prime, so we want to transfer it in the same way. So this becomes R del psi over del k dot delta theta prime minus big R del psi over del k prime dot delta theta. So, but this is not done yet. There is something more. So that's plus big R del psi over del V dot R prime cross delta theta. Okay, and of course then you have this extra term, maybe I should write here, minus PE1 dot delta RL. Okay, now I want to keep the integral terms separate and boundary terms separate. You see this one, for example, the whole prime, it can be integrated, right, and you get boundary terms. But this one you can't integrate. So we get, so let's first keep the boundary term. So this is R del psi over del V dot delta R at 0 and L. So you get the boundary term. And the boundary term from the bottom. Okay, this with a minus PE1 dot delta RL plus the boundary term from the bottom, that's R del psi over del k dot delta theta 0 L plus the remaining terms. So you have minus 0 to L big R del psi over del V whole prime dot delta R minus 0 to L big R del psi over del k whole prime, and you see this term, you see it's a scalar triple product, right? A dot B cross C. What if I interchange this? That was minus delta theta cross R prime, and then you further bring the cross product over here. So you can do that business and you get okay, so we are really over there. Can you see that? That's the second term. Now can you tell me what should we do? How do we extract the Euler-Lagrange equation? So you see that we have got delta R, delta theta separate, and delta R and delta theta are two independent perturbations. Delta R is for the center line and delta theta is for the rotation, and since they can be arbitrary, the integrand must vanish. So that gives us the Euler-Lagrange equations: big R del psi over del V whole prime is equal to 0, and this gives us big R del psi over del k whole prime plus R prime cross big R del psi over del V equal to 0. And what about the boundary condition? Have a look at that. Remember, we had that cantilever problem. So what can you say about the perturbation in delta R, the perturbation delta R, delta small r at s equal to 0? So it's a clamped boundary condition. You are not allowed to perturb at s equal to 0, right? So the perturbations have to satisfy the boundary condition. So that means delta small r at 0 is equal to 0, isn't it, for this particular problem? And similarly, delta theta at 0, that's also equal to 0. You are not allowed to even perturb the rotation. Cross section is fixed, it can't rotate further. So at 0, the perturbations have to vanish. That's the admissibility criteria on the perturbations, right? But there is no such restriction at s equal to L. Here it can even move and also rotate. There is no restriction on perturbations at s equal to L. So when you plug this in over here, you see the 0 term goes away because this is delta r of 0. Similarly here, delta theta of 0. So that's automatically vanished. So here you have at L, right? So you get big R del psi over del V minus PE1 dot delta R at L plus big R del psi over del K dot delta theta at L. So, that is also equal to 0. See, the whole thing perturbation had to be 0, the whole first variation, but then you already found these are 0. So, this was remaining, that also has to be equal to 0, which I wrote down over there. And what can you see from here? Delta R at L is again arbitrary. That gives us the boundary condition that big R del psi over del V is equal to PE1. And the other one, since delta theta at L is also arbitrary, they are both independently arbitrary. So, big R del psi over del K is also equal to 0. Okay, so we have gotten the Euler-Lagrange equation as well as the boundary condition. So, now we have to compare this with the equations that we got from the Newton's law, right? They have to be the same. All right. So, this will be the last slide, do not worry, just few more minutes. Okay, so your equations from Newton's law was n prime plus n hat equal to 0 and m prime plus r prime cross n plus m hat equal to 0, right? Can we make a comparison between these two equations and the equations up there? We do not see the distributed load and distributed couple present there. Why? Because in our potential energy, we had not taken that thing into account. These are due to external loads, right? We did not take the potential of these external loads. If you had taken them, then you had gotten the extra terms there. But since you did not take it, so they did not show up here. Okay, so let us forget about them. So, they are not present because we did not consider it in our cantilever problem. See, there is no distributed load or couple, right? So, it did not come there. Then you compare these equations with what you have over there. And what do you get? That n is equal to big R del psi over del V, and m is equal to big R del psi over del K. And if you use that in the boundary condition also, you see this is the boundary condition, that tells me n, the contact force at L, is equal to PE1. That is what you have in the problem also, right? Contact force at L is equal to PE1. Similarly, this R times del psi by del K, which is moment at L is equal to 0 because it is moment free at the other end. Okay, so the whole thing was done to establish these two relations. But of course, you learned lots of things. Okay. So what you see is that you take the derivative of psi with respect to v, you get the forces. Of course, you have to multiply with rotation. If you don't multiply with rotations, then del psi by del v will be such that del psi by del v1 will be the shear force, the force along d1. Similarly, del psi by del v2 will also be the shear force, and del psi by del v3 will be the axial force. We'll work that out more in a more nicer fashion in the next class. Okay, so maybe I'll stop here. So that is it. Okay, see you in the next class.